Hello wonderful person, this is Anton, and today we're going to discuss a somewhat intriguing study in regards to the limits of measurement of time. And specifically a kind of a fundamental uncertainty in the universe itself that seems to prevent us from measuring time super precisely. But this doesn't mean that there is some kind of a flaw or some kind of an error in the time measurement device. It just means that by itself, the universe seems to prevent us from measuring time too accurately. And so let's discuss this new study by Nicola Bertolotti and the team you see right here in a little bit more detail. But first, let's discuss exactly what this is based on and why right now this proposition makes a lot of sense. And that's because it's based on the most successful theory in modern physics, the idea known as quantum mechanics. And essentially the idea that's the foundation for pretty much most of the modern technology around us. Anything from microprocessors inside the device you're watching this on, to various types of lasers, various types of internet cables. Pretty much everything today depends on quantum mechanics or quantum physics. But despite its success, there is a giant gaping hole in our overall understanding of this theory. And especially because there is something referred to as the measurement problem. Simply because in the quantum world, things are always kind of fuzzy. And so particles like electrons don't exist in one spot, they seem to exist in a kind of a superposition of many places at once. This is what you see right here, and it's essentially what we usually refer to as the wave function. But the moment we measure them, or I guess the moment we look at them, that fuzziness vanishes and they become solid and classical. They turn into individual particles. And well, the thing is, the standard explanation in physics is, well, it just kind of happens. Don't worry about it. But that's not obviously enough for a lot of physicists, and some physicists are a little bit worried because it just does not make a lot of sense. They really want to know why it happens and what exactly happens as well. And while this particular recent study that was recently published in the Physics Review Research possibly provides us with at least one explanation, suggesting that the answer might be hidden in the way gravity affects the very flow of time itself. And so today we're going to discuss some of these discoveries behind the spontaneous collapse, and why gravity might affect some things, but also how this fundamentally puts a major limit on our ability to measure time itself, basically making time a little bit fuzzy. But to understand this, we first have to discuss one of the principles in quantum physics, the spontaneous collapse model, also known as the objective collapse or dynamical reduction theory, that tries to explain or tries to propose solutions to these ideas of quantum physics. Now you can read about some of them in one of the articles in the description, but in a nutshell, this is basically an attempt to explain what happens to a lot of matter in the universe. Now in traditional quantum mechanics, the wave function evolves smoothly and then disappears suddenly when the measurement occurs. This is what we refer to as the wave collapse. But in that spontaneous collapse model, which was actually proposed in the 1980s, the suggestion is that the collapse is not triggered by an observer, or to be more exact, it's not the result of measurements or some kind of a conscious observation. It really happens constantly and spontaneously everywhere around us. And so, for example, imagine a single atom. According to these models, that atom is usually being poked by all sorts of background noise that sometimes forces it to choose a definitive state. It's trying to be a wave, but everything around it prevents it from becoming a wave through these constant interactions. And for one atom, this might only happen once every few 100 million years. But for a large object, like for example, a dust grain or obviously a person, something containing trillions of atoms, a lot of these interactions happen billions times per second, and so the object remains in the particle state and never becomes a wave. Which is why we don't really see people in two places at once, or the Schrödinger cat does not actually appear alive and dead at the same time if we're talking about a real cat. And so this amplification mechanism ensures that a lot of larger objects collapse into a solid state almost instantly. And though here there are quite a few additional propositions or slightly different models and explanations, for this study and for this explanation, the two biggest players are known as the DOC-Penrose model and the continuous spontaneous localization model, both of which you can learn about in the links in the description. And while they do differ slightly in the math, they both have the same idea. They're trying to explain this fuzzy world by giving us equations that turn the fuzziness or the quantum state into the solid classical reality. Okay, but where does the idea behind gravity come in? Well, this is where things get just a little bit more interesting, because at least one idea, championed by Sir Roger Penrose and Lajos Diosi, proposes something somewhat intriguing. Specifically, they argue that the quantum mechanics and the general relativity, the theory proposed by Einstein, simply do not like to coexist and don't like each other. And that's because, according to Einstein, matter, any matter, for example a tiny ball or a large planet, tends to curve space-time and creates these very specific perturbations in the fabric of space-time itself. And so if some kind of a particle that has not collapsed yet, and that seems to exist in a superposition of two different locations, finds itself inside this curved space-time, things become just a little bit complicated. And that's because it effectively tries to curve space-time in two different ways at once. And so if there is some kind of a particle in superposition, and it seems to exist in two separate locations at once, it effectively, by definition, will try to curve spacetime in two locations at the same time. And curving spacetime in two different ways at the same time creates a kind of a bizarre tension, with the physicists suggesting that the spacetime tends to dislike this tension and does not keep particles in this state for too long. In other words, a particle in a superposition state cannot stay in this superposition in two separate locations for too long. Eventually its quantum state will crack and the wave function will collapse into one of two spots in order to resolve the conflict. And so here this is often referred to as a kind of a gravitization of quantum mechanics. It sort of resolves why we see a lot of particles and not as many waves, and also suggests that gravity might be the fundamental reason why the universe appears solid all around us. And so here it's not about observations, measurements, or looking at the universe. It's really about the very fabric of space-time itself. Space and time refuse to be in two states in two different locations at once. Which essentially brings us to this new study and this new proposition from 2026. And so here we have this study by Nicola Bortolotti and an international team that tried to look at how these collapse models predict additional features, and specifically they wanted to ask a concrete question. If the gravity causes the collapse of particles around us because it just does not allow them to be in two different locations at the same time for too long, here, since this is also in regards to space, it doesn't actually tell us what happens to time. In other words, it prevents the location in space, but does this also affect time in some way? And especially because, according to the general relativity, time is not some kind of a fixed background. It's directly linked to space, and it's thus linked to gravity. And so if the gravitational field has these very tiny fluctuations or noise that eventually cause quantum collapse, then the flow of time itself must also be fluctuating and should be noisy. Or essentially, the time itself should contain a kind of a jitter that's fundamental because of quantum physics and would prevent us from measuring time super accurately. And so in essence, this particular study calculates the fundamental limit on clock precision, the precision beyond which we cannot make accurate observations. And so they found that if these collapse models are correct, there seems to be an ultimate limit for sure, with some clocks not being able to measure time below a certain amount, even if you build the most accurate clock in the universe. And it's really because of this bizarre space-time uncertainty. But I guess the question is, okay, so how accurate are we talking about? And how does this compare to some of the most accurate clocks we have right now? Well, here scientists discovered that this fundamental uncertainty is actually pretty small. And it technically does depend on the model. For example, if we use the Diosi-Penrose model, the fundamental time uncertainty seems to be roughly around 10 to the power of minus 31 seconds over the course of one single year. Or basically, in one single year, there's this really tiny uncertainty of 10 to the power of minus 31 seconds. Whereas for the continuous spontaneous localization model, the uncertainty is a little bit larger at 10 to the power of minus 28 seconds per year. And so both models contain the uncertainty and suggest that this is a characteristic fundamental to the universe itself. But how does this compare to some of the most accurate clocks? Now you can actually learn about this in some of the previous videos in the description where we discuss the technology and how it works. But in essence, today some of the most accurate clocks are optical atomic clocks. They essentially use lasers to measure vibrations inside ultra-cold atoms of things like, for example, strontium. And so for some of these strontium clocks that measure the vibration of strontium atoms, they're usually accurate to about 2 to the power of 10 to the minus 11 seconds per year, which is about 1 quintillion times less accurate than the calculations from the study. In other words, we need to create a clock that's quintillion times more accurate first before any of this will matter. And so this has no impact on modern technology. And that means that everyday timekeeping, such as GPS networks, that are used for a lot of different reasons in modern technology, seem to be pretty safe. But because of this discovery, it also gives us some new ideas on how to test some of these quantum propositions and to find out if some of the quantum theories are true. And that's because most interpretations of quantum mechanics are sometimes purely philosophical. They don't really contain any physical proof and, by definition, are extremely challenging to prove or to find evidence for. However, because collapse models make concrete mathematical predictions, especially about time uncertainty, this paper now provides us with the theoretical blueprint for how physicists might actually rule out some of the collapse models by actually pushing the boundaries of clock precision and by creating clocks that are even more accurate, which can then tell us which model is correct and which is not. At the same time, because these theories connect quantum collapse to gravity, it might also help us move a little bit closer to this unifying proposition referred to as quantum gravity, essentially creating some kind of a model that might explain the universe all at once. Now, obviously, we're not even remotely there yet, but this study is definitely a start. But the question is, can we actually prove that these collapse models and collapse theories are correct? Well, according to these models, because of these constant interactions with gravity, it should also produce a kind of a side effect, a tiny amount of heat or a kind of a glow, because the noise that causes the collapse also gives particles a tiny permanent motion in a random direction. So essentially it produces a kind of a Brownian motion that technically should be detectable with something extremely precise. And to find this, at least one team has actually gone deep underground to places like Gran Sasso Mountain in Italy, where they use massive detectors made out of high-purity germanium in order to see if anything here can show us this glow. Now, right now, this has not been detected yet, so actually this invalidates some of the collapse models and even places a strict limit on some other models. But this is also because these observations right now are not that accurate, and some of the experiments might have to rework this just a little bit. And so scientists believe that some of this glow might only be visible at specific wavelengths, which are just a little bit hard to detect. But the point of all of this is that, well, at the moment, this transition from the fuzzy quantum state to the classical reality all around us is still one of the greatest mysteries in science. And though these spontaneous collapse theories try to explain and try to solve this, even proposing that gravity and space-time seem to control everything, right now these are still very theoretical and there's no actual evidence yet. But assuming these models are correct, it means that the time itself is also inherently fuzzy and uncertain, and we'll never be able to create a super accurate clock that can be more precise than this limit. And though it's not going to affect our daily lives, since timekeeping is so important for the modern society, knowing that there's this limit is also very important, simply because it's going to prevent future errors and future uncertainty. But even if these models do fail and none of this is correct, this still forces us to sit down and to basically think about these theories and to try to figure out how the quantum world connects to the space-time world or the world of theory of relativity, and how we can possibly unite them into one grand proposition. On that note, once we discover something else, we'll come back and talk about this in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.